Okay, this is our second video for 4.10, solving logarithmic equations using the properties of logarithms. So what we're going to look at here are the properties where we do the power inside the log. Recall the other day we had property where we said if we had log base b of a to the x power, that exponent can come out front and multiply times the log base b of a. That's going to allow us to solve some equations and make things easier on us. Let's look at an example where we have log base 4 of 3x minus 2 to the third power equals 6. Now, if we just converted this to exponential form, we would have a third degree polynomial we'd have to solve, which would make it difficult. But because of this property, we can bring that power that's inside the log out front and multiply. 3 times log base 4 of 3x minus 2 equals 6. And now, because this log base 4 of 3x minus 2 is just a number, it's the power of 4 that would give us 3x minus 2, we can divide both sides by a 3 and end up with log base 4 of 3x minus 2. We divide through 6 by 3, we get 2. So now we have a simple equation, a logarithmic equation we can convert to exponential form like we've been doing, where it's 4 to the second power equals 3x minus 2. This is 16 equals 3x minus 2. We add 2 to both sides, you get 18 equals 3x. Divide both sides by 3, get x equals 6. And if we go back up and check and make sure that we don't get a negative inside the log, we get plug 6 in, and we get 18 minus 2 at 16. This is a valid solution to the equation. But rather than having to solve a third degree polynomial equation, all we had to do is solve a simple linear equation once we use the properties of logarithms. We're going to do another one where we have ln of x squared minus 7 to the fifth, equals 10. Now here again, we could raise and convert this exponential form, but then we'd have this fifth power of a quadratic polynomial. We'd end up with a 10th degree polynomial equation. No fun. That could be fun. But anyway, we can use this property first and say 5 times ln of x squared minus 7 equals 10. Divide both sides by 5 and get ln x squared minus 7 equals 2 when we divide 10 by 5. Now we can convert to exponential form and get e squared equals x squared minus 7. And if we add 7 to both sides, we get e squared plus 7 equals x squared. Take the square root and we get plus or minus the square root of e squared plus 7. And this equals x. Now, we need to be careful here. The positive root, x equals square root of e squared plus 7. When we square that, we get e squared plus 7 minus 7. That's going to give us ln of e squared raised to the fifth power. There's nothing wrong with that. That's a perfectly good one. We need to make sure, though, that when we plug in negative square root of e squared plus 7, that we don't end up with a negative inside the log. So now when we square that, we're going to square it anyway. So it's going to end up being, even though we're going to plug in a negative, it's going to be squared, and we're still going to get e squared. So these are both valid solutions. Because when I square a negative, I get a positive, and I'll still get e squared plus 7 minus 7. I'll still get e squared. So that's going to be good. Let's look at one more in there. Let's look at a little different one. And let's look at log base 2 of 8 raised to the 5x plus 3 power. And let's say that equals 25. Now this is a little more interesting because now we have the function of x as an exponent inside a log. But it's the power, the property still applies, where we can bring this exponent out front and multiply to get 5x plus 3 times log base 2 of 8 equals 25. Now we know what log base 2 of 8 is. That's the power of 2 that gives me 8. So log base 2 of 8 is 3. So this becomes 5x plus 3 times 3 equals 25. I'm going to come up here. We'll have a little more room to finish solving this. We can distribute that 3 and get 15x plus 9 equals 25. Subtract the 9 from both sides and get 15x equals 16. And then divide both sides by 15. X equals 16 fifteenths. We have 8 raised to a power. That's always going to be a positive number, so we don't have to worry about the extraneous solutions here. But that would be the solution that would give us, that would make that equation true. And these are the ways that we'll use the power inside the log property. Now we'll look at the property where we had the sums of the logs with the same base. Recall that we had the property yesterday. We had log base b of x plus log base b of y is equal to log base b of x times y. Let's do some examples with this one. Let's look at the equation. It says log x plus log x minus 21 equals 2. Recall when you see the log without a base written there, it's an understood 10 base. So we have log base 10 of x plus log base 10 of x minus 21 equals 2. This follows that property, 2 logs, same base added together. So we can multiply what's inside the logs inside a single log. We get x times x minus 21 makes x squared minus 21x. If that equals 2, now we can convert this to exponential form and get the base 10 raised to the second power equals x squared minus 21x. 10 squared is 100. We have a quadratic equation. We can solve that by getting everything equals 0. X 0 equals x squared minus 21x minus 100. This is a factorable expression, so we can write x minus 25 times x plus 4 equals 0. That lets us know that x equals 25 or x equals negative 4. If we plug in 25 back in the original expression, we get log 25 plus log 4. Nothing wrong with that, both positive numbers inside the log. If we plug in negative 4, though, we get log of negative 4. And we know we can't have a negative inside the log. That's an extraneous solution. We have to throw that out or we'll get the problem wrong. Let's do another example. Let's do ln of 3 plus ln of 2x plus 1 equals 2. Now this one, ln 3 is just a number. We could do 2 minus ln 3, but that would give us a decimal approximation in our calculator. We can use this property again now to say that this is going to be ln of, and multiply these together to get 6x plus 3 equals 2. Now we can convert to exponential form and get e squared equals 6x plus 3. Subtract 3 from both sides, e squared minus 3. Oops, getting a little ahead of myself. Equals 6x. Then we can divide both sides by 6 and get e squared minus 3 over 6 equals x. Now we need to consider again, if we plug it in, we're going to get a positive number. Now e is 2.718, something like that. E squared is going to be a larger number than 3 because it's going to be larger than 4. So that's going to make this a positive number. And if I plug a positive number in, multiply by 2 and add 1, I'll get a positive number. So this is a valid solution. Let's do one more with that. Let's do one that looks a little scary, but you'll see it's really not scary. Let's look at log base 30 of x minus 3 plus log base 30 of x minus 4 equals 1. That 30 is a base, looks kind of scary. The two different linear expressions look a little scary, but we're still following the same property. So we're going to do log base 30, and we're going to multiply x minus 3 times x minus 4. When I multiply this, I just distribute, and I get x squared minus 4x minus 3x plus 12. It still equals 1. Let's go ahead and clean that up. Get log base 30, x squared minus 7x plus 12 equals 1. Now I'm in the logarithmic form. I can convert to exponential form. I get 30 to the first power equals x squared minus 7x plus 12. If If I subtract 30 from both sides, I get 0 equals x squared minus 7x minus 18. This is factorable. I can do x minus 9 times x plus 2. Negative 9 and 2, multiply, make negative 18, add to make negative 7. This tells me, we'll come up here now where I have a little room, x equals 9, or x equals negative 2. If I plug in 9 to the original expression, I get log base 30 of 6 plus log base 30 of 5. Nothing wrong with that. It's a good solution. If I plug in negative 2, though, I get negatives inside log, so that's an extraneous solution. The solution to my equation is x equals 9. Last property we're going to talk about with equations, the difference of logs with the same base. Remember yesterday we had the log base b of x minus log base b of y gave us log base b of x over y. So if we have an equation that has log base b, let's do a different base. Let's just do log. Let's say we have log of x minus 7 minus log x minus 9 equals 3. We can bring these two in a single log. Remember, the base is 10 when we don't see it, of the first expression over the last second expression. This equals 3. So now we can convert this to exponential form. We get 10 to the third equals x minus 7 over x minus 9. 10 to the third is 1,000. When we have a variable in the denominator of a fraction, we need to multiply both sides of the equation by the denominator. We can do that because this cancels on the fraction of the denominator, and we get 1,000 times x minus 9 equals x minus 7. So 1,000x minus 9,000 equals x minus 7. If we subtract x from both sides, we get 999x. And if we add 9,000 to both sides, we get equals 8,993. Bring this up here, we have some room. Now we divide both sides by 999, and we get x equals 8993 divided by 999. If we plug that in here, that's definitely larger than 7, because 7 times 1,000 would be 7, or 1,000. 7,000 divided by 1,000 would be 7, and this is larger than that. This may not be a valid solution because it may go in here. Let's type this in the calculator and subtract 9 from it. Let's do 8, or just see if it's larger than 9. 8993 divided by 999. That is larger than 9, just barely. It's 9.002. So if I plug this in here, it will give me a positive number. If I plug it in here, it will give me a positive number. So this is a valid solution. Let's do another one here where we get, let's do log, let's say this is going to be log base 3 x minus log base 3. Let's do x minus 2. Let's do 2x minus 2 this time. Minus 3 equals 2. Let's see what happens here. Understand we can sometimes get no solution. May not work this time. Just made this one up. So this is, again, a place where we can use log base 3. We can use that quotient, x over 2x minus 3, and that equals 2. We can convert to exponential form and get 9 equals 3 squared, it's 9, equals x over 2x minus 3. If I multiply both sides by 2x minus 3, I get 18x minus 27 equals x. Now subtract x from both sides and get 17x. Add 27 to both sides and get 27. So x equals 27 over 17. If I multiply that by 2, 27 over 17, let's make sure that 2 times that is bigger than 3. So 2 times 27 divided by 17. That's 3.176. So that is definitely going to give us a positive number here. It's a positive number here. This is a valid solution. Those are using those other properties, ways to solve equations. And that's our lesson 4.10.